present as we go. Please give me a shout if you don't see a slide moving and so on. My name is Reza Nejabati, and I am head of the quantum research and quantum labs in Cisco and based in USA. So what I am going to talk today about is to review very briefly in a couple of slides what is the state of play for real deployment of quantum networks, and what is the Cisco vision for quantum networks, how we see quite significantly different from what is already in the market. And then I go and show that how we are developing a quantum network for scalable quantum computing, and then a little bit allude what our activity toward the quantum networks for next generation network when it comes in play. And then I a little bit advocate our quantum network digital twin, which becoming available soon, especially for academics if they would like to use and collaborate on that. So moving on the a couple of introductory slides. If you look at the quantum advantage, we see that already the security is there. We can have a no cloning property of quantum and have a quantum key distribution. There are products in the market for that, and QKD is very well known. The other thing is a quantum computing. Quantum computing obviously uses superposition of qubit and create a more powerful computer for some applications or some algorithms. Not universal, definitely. However, this is more at the research at the moment, but I strongly believe in 3 to 5 years' time, we will see some useful commercial availability of the reasonable size quantum computers. If you look at the sensing, also a quantum effect is very sensitive to environmental changes. So you can use that for quantum sensing. And quantum sensors are pretty mature, and there are available and widely used, especially in military or even science. But for the commercial deployment, like a thermal sensing and location sensing, also becoming available. And then I am sure all of you have heard about the multiple experiments and research on the doing entanglement and teleportation, which creates a new angle of the networking using the quantum properties of quantum physics. So if you look at the state of the play for today's real-life quantum networks, is mainly point-to-point. As far as I know, and we know in Cisco, is the industrial deployment is limited to QKD. And normally they use either free space, satellite, or perhaps dedicated fiber or frequency band. And essentially they use the QKD, just exchange the key. And you can see example of that. The famous example of real deployment is China's national quantum network, is pretty big quantum key distribution network. And then we have a British Telecom deployed a ring in City of London and provided as a service QKD network for any customer that would benefit from it. So as I mentioned, the current issue is that is point-to-point, static, no dynamicity, no switching, no routing. A specific use cases purely on the QKD. And to be honest, for QKD, I wouldn't see it as a full security solution for especially real life and industrial use cases. It's just secure the optical link, doesn't secure end node, and there is no extension to wireless. So need a dedicated hardware, dedicated fiber, and the frequency band, and very large guard band between your really traffic channel and quantum channel. As such, I would consider at the moment it's not scalable, it's very costly, and it is not robust enough or comprehensive enough it can consider as a security solution. So what we see as Cisco for quantum networks. Okay, as I mentioned, that the security, computing, and sensing quantum domains or using quantum technology for these 3 areas is becoming mature. So if we have a network that connects them together, and then in Cisco, our view is if we can somehow connect them together and create them a mechanism that can scale them and provide them as a service, especially quantum computers. We call it quantum cloud computing and quantum data center. and then also create a network that can create a distributed sensing for quantum sensor. That's something that we are focusing on, that to build a network for that. And we are basically developing a quantum network, which is entanglement, dynamic. It can coexist with classical and in the same fiber. It has a full stack of control and protocol on top of that, and is a multi-tenant and multi-users. And basically, that's what in Cisco we are building for quantum network. Let's a little bit further detail it, that we go certainly beyond security. Security is not something that we see is going to be clear application for quantum. And we want to focus on distributed sensing and computing, multi-tenant and virtualizable. And also we want to be dynamically switched and routed. So it's important for us. Cisco is a networking and switching company, and we want to keep what we are good at it and create a network and switch that support quantum information switching and routing as well. So let's see what we are building, what we call it dynamic quantum entanglement network fabric. It has a quantum switch. There are several elements we are developing currently at different level of maturity. We have a quantum measurements, quantum entanglement source, entanglement swapping, and quantum memory. And then these are the hardware part. On top of that, we are developing the full stack of the network protocol for entanglement distribution. So that's where our focus of at least my team in Cisco is. Let's see what we have done so far. Entanglement photon generation is not a difficult one anymore. I mean, it's pretty easy to do that. You can have a photon source, and if you generate entanglement photons, you can basically send it to 2 different points. And if you do the measurements, you can use all the properties of entangled photons. How we do that? Usually, you get a laser pump and then inject it to a nonlinear material, Chi2 or Chi2 or Chi3, depends on the properties that you want, and create your entanglement photons normally probabilistic manner. And then you put it in if you can develop a switch that can route this entire photon, essentially you can create a network. If you have your source and switch in the middle, you consider you can connect different nodes with it, and you can create a logical mesh of the entanglement distribution network. That's essentially we aim to build. Let's see where we are at that. For our entanglement source, obviously the easy way that most laboratory they use nonlinear material based on crystal, but that's not gonna make a very effective commercial solution, if you like, and you can ship it to the customer. What we are looking at, ultra bright chip scale source that we can generate order of the hundreds of millions entanglement per second, and also we can have a low power. So, and we can have a multiple of this source in a small footprint. We are working in various solutions. Some of them that I can expose here is based on the compound semiconductor, specifically aluminum gallium arsenide surrounded by silica isolator. And we use a ring resonator for generating that. The ring resonator essentially give us the spontaneous 4-wave mixing, which can generate get a laser pump. If we inject to that, we can create using that nonlinearity of 4-wave mixing, and basically create entanglement photon pairs. And that's something that we found quite efficient. It can gives us the broadband range over both C-band and O-band, and is very power efficient, and it's quite efficient. So this is another figure that shows that basically is a ring resonator. We inject the pump laser to it, depend on the wavelength of the pump. Obviously, you can shift your frequency comb, and then you can get your pair of entanglement photon. You can engineer your ring resonator, depends on the basically how do you want to be a space of your frequency comb, and what would be you want to be an entanglement generation rate, and the quality you want, and based on the material you have. That's something that we are engineering to build the most efficient way for us. This is the lithography picture of the 8-channel source. At the moment, we are we are having basically works at the both 1300 and 1550 nanometers frequency range that generates entanglement pair source for us. Now, once we have this entanglement source, the problem is that if you want to create a network and use it, you need to be able to measure it. And if you want to do effective measurement, you need a very sensitive detectors. And normally, the sensitive detectors means that nanowire detectors or some sort of photo detectors that are submerged in a cooling liquid that bring the temperature down to make them sensitive and make them efficient. So that's something that you cannot expect that in any setting you have a large number of these devices distributed. It's expensive, it's difficult to maintain. And that's something that we want to see how we can overcome that. One of the ways that we try to create a network architecture that some of these expensive sources like a detector, like memory, are shared using the switch as a part of the switch. So one of the things we are developing in quantum entanglement switch, the characteristic of the switch is that is a non-blocking, has a high connectivity. It can support multiple mode of entanglement, mean timing, frequency, mean polarization-based entanglement. That's something is very unique to Cisco. I'm not aware of any academics or otherwise to be able to do that. It is very highly accurate and efficient in terms of the loss and jitter. And also, we are working toward that integrating and plugging these expensive devices so that it can be shared. I'll show you exactly how we share these expensive devices later on. And also, we are working on a version of the switch that can be based on the semi technology that we are using already for our classical data switching to have both classical and quantum, at least in the same chassis. So we have two versions of the switch. One switch was just switching the entangled pair photon signal and idler here. And the other type of the switch is also doing the heralding of that, which is the heralding that we use it for sharing the devices that we want. At the moment, we are working at multiple material from thermo optics to electro-optics modulators to lithium niobate to silicon to combination of lithium niobate and silicon. Still, we are at the experimental or trial phase of this. We have a various version of this switch. My hope is that we are converging to the final solution, which would be based on the both lithium niobate and silicon combination of that, a composite type of the switch that works a wide range of frequency based on the electro-optic modulator that we are converging toward, but still I am not one of the that's essentially is one of the candidates that we are bringing up. But there are several other technologies also we are working, which I show you later on at the functional diagram in my slide. So once we have this switch, we basically also we needed to build a protocol stack on top of that. We are developing entanglement distribution protocols, various of for different application, entanglement routing, scheduling, and also how we fit this with the existing classical channels is also important for us. So let's say that what are the use cases? That brings a little bit more flesh to what I explained to you, how we use these things. One of the very, very important use cases, strategic use case for us, is the scalable quantum computing, specifically quantum data center. So what is a quantum data center? As this name says, putting the quantum computer in a smaller size together in a warehouse, connect them together using network. Why we need a quantum data center? Because a useful quantum computer, 20 million qubits, roughly give and take, a few millions, but that's the order of size we are talking. And if you look at the monolithic challenges that we have in quantum computer today, simply is not realistic to think that you build 20 million qubits. Even if you can, it's not possible to operate it in a reasonable manner. So a million qubit processor needs a full football pitch size cooling system. So you can imagine 20 million qubit, what would be that. So that's why I think the data center is important. That's why in Cisco, we are building a full-fledged network for that, which I will dig to it a little bit more. So let's see, we have a two processor here. I want to explain what we do exactly. Two quantum processors. When you want to connect the two quantum processor, you have to basically set up your computing capability for communication. So you have, see, I have a red qubits, which is allocated to communication, and green one allocated for computing. So processor use the red communication qubits for communicating with each other, and then quantum green for processing. And if you want to do the distributed processing in a data center fashion, you need to entangle to processor using these communication qubits. That's where we are developing the network. So not only we are developing the physical layer, but also we are doing the software stack on top of that. Why software stack is important? Because assume that you have a quantum application, for example, drug design. You based on that, your quantum mathematician, your quantum scientist basically develop a quantum chemical calculation for you, and then based on that, you come with the quantum circuits. Any useful quantum circuits today, you cannot run it in single processor, even in 5 years' time with the current projection. So what we develop in Cisco, we try to come with a mechanism to break these circuits to multiple circuits and try to map them to the processor that we have. And then we build a network. We do that by considering what would be the effect of the network and the penalty that network introduces. That's because Cisco compiler. So we are I believe we are the only, again, both in both the scientific academic arena and also industry, that doing the quantum compiler. There are many quantum compiler available, but our quantum compiler is fully considered the network that you need to connect the processor together for distributed computing. So that's something that is quite unique. So this network-aware compiler consider the decoherence time of our qubits, consider link loss, consider that how you organize your data center in terms of the processors, in terms of the processing qubit versus communication qubit, entanglement fidelity, and then how you partition your circuits. So you saw that I show our switch is based on the compound semiconductor and use multiple materials. And the reason for that is that essentially we have a two version of the switch. One switch is sit on top of the rack, and the other switch between the racks. As you see, I simplified the architecture here. This is not exactly architecture that we developed, but gives the message. For inside the rack, we are using it's very short distance. We are using near IR frequency for communications. And the reason is for that, I go to next slide, explain that. And for between the racks, we are using telecom range. Okay, let's a little bit dig to this a little bit better. So why we are using near IR for inside the rack? The near IR give us the capability that we become compatible with most of the atomic-based quantum computers. So most of them works at near IR range. So therefore, we can be compatible with that. And also, entanglement swapping and detection is much more efficient at those frequencies. However, developing the transmission at those frequencies, as you know, is very inefficient. And also building the switch is a big challenge there. So we are coming with that with a special type of fibers, and also the distance, very short distance between our switch and the processors. However, we get an advantage. We can directly basically inject our photons inside the CPU and use the cavity in our processors for entanglement. And then for our swapping inside the rack and then do the teleportation between the two processors, that's become more efficient in that frequencies. But between the racks, simply the distance is not allows us to go near IR. So between the racks, we are using the the telecom range and our telecom switch. And also the detectors here are all basically, and BSM are very expensive devices and based in cryogenic systems. So we try to reduce the number of them and share them between the racks. So that's basically to give you a rough idea. I cannot expose the detail of our architecture, but that's essentially the principle of our design. So here it shows another example that how we work inside the rack and outside of the rack for communication between our processors. Interestingly, I want to show here our communication between the two racks. Two racks, the box that you see called ES is the entanglement source. So we have one version of an entanglement source, which is quite unique to us. Cisco can generate a near IR, two photons, entanglement photon, one at near IR, the other at telecom range. So we use this unique entanglement source to basically create an entanglement relationship between the processor in two different racks. So that's also very quite unique to our Cisco technology. Now, our Cisco compiler, I said that is quite, actually is very advanced at the moment. We call it Q Orchestra. It does the circuit partitioning. It creates a graph-based workflow for your, and then do the scheduling and protocols and do the mapping to your qubits inside the data center, and also schedule your network for communication per qubits. We are using various algorithm and protocol based on the major quantum computing vendors in the market, which we collaborate with them to see which one fits the quantum computing technology the best. So this can show you example. For example, the left-hand side is a part of the QFT circuit, the quantum Fourier transform circuit, which is quite common circuit in many algorithms in quantum computing. And that gives you a graph that our compiler creates, and how the graph is mapped for communication between rack and inside the racks for various processors. So one of the things that I said gives our compiler, we can optimize based on the quantum computer that we have, how many switch we need, because the important thing is that for us to reduce number of our detector and swapping events or teleportation events at the telecom regime. So for us, therefore, when we get a circuit, we try to see how we have to architect our quantum computers connectivity to achieve that. Our compiler helps to do that. This shows that, for example, how we model using our compiler shows that if total number of our telecom Bell state measurement, which is used for swapping and teleportation, per aggregation switch, if we increase it in more than number of 10, doesn't make to be honest, a lot of difference. Depends on the number of your communication qubit, which is NQ here is that, which is start from then 2 to number of 10. So we found that for certain circuits, we can use this compiler to basically decide what type of architecture we want to use for connectivity between our communication, and create an optimized topology for that. At the moment, the compiler is very powerful to give us the network design, but at the moment, we are still working that in a case that we can create a universal architecture for all type of the circuits. At the moment, our data center has to manually, or some part of it is fixed, depending on what type of the processing we want to run and what type of the computing technology you are using for that. But we are overcoming that part as well. This is in press for publication. If you are interested, you can contact me. I will tell you where to find more information about this. So eventually, our data center
Hi, Reza, we cannot hear you anymore.
Yeah,
Hello?
a small number of the processor. I am finishing in a minute. Yes. Can you hear me?
Yes, now we can hear you. Please continue.
So our data centers are basically has a classical network and quantum networks. At the moment, we are working to connect the 100 qubits processors together, a few of them, and create a data center in our lab in Santa Monica based on this architecture. A little bit I want to say about, because I get quite this question, what is the position of Cisco for quantum security? We don't advocate quantum QKD or PQ. I mean, we advocate, basically, we have both, we have a PQC solution for security for next generation network, post-quantum cryptography solution. We don't advocate QKD as a application because of the US government position on that. Nevertheless, if somebody wants to use to be quantum safe for next generation network, either has to use PQC and QKD. Cisco has a solution for both of it. Your entanglement network can be used for key distribution, a small scale network, metro size network. However, is up to the customer if they want to deploy that. But what came as a byproduct of activity in my group is a quantum random number generator, which we use the quantum vacuum noise to the quantum random number. We have a quantum random number generator, which is a pluggable, and you can use it as a random seed for your PQC or QKD. This is available now, and you can see the picture of it. This is the discrete version of it, but it is available at the SFP size pluggable. But the feature of is that is the fastest available in the market, 100 gigabit per second random number at quantum random number it can generate. So our view is that at the hardware side, we develop a quantum entanglement distribution network. At the moment, is a short distance for metro scale. We are working on repeater. I didn't have a time to present here about our repeater, but we have a repeater activity. I don't see it's coming very soon in the next maybe 3 to 5 years time it will come. But once that comes, we can extend our entanglement distribution for larger network. We mainly advocate our network for quantum computing interconnect at data center level, but people can use it for security, a small range as well. We have a whole software stack for the key distribution if somebody want to use entanglement-based QKD as. And it can support PQC and QKD all together. Now, something that for academics folks maybe is useful, this quantum network digital twin for quantum network planning, modeling, and upskill training. What we have a live testbed in 2 of them, in fact, in Santa Monica and San Jose in US on quantum networks. We have a very advanced quantum network simulators. Our devices also modeled as an emulated version inside our, we call quantum network emulator, our switch, our processors that we work with it, our source, our detectors, and all of them available in a cloud we call QNet Lab. And people can, you can see the picture of it. People can come and basically create a network, use it for QKD, use it for distributed quantum computing, use it, and you can use various versions of the protocol. You can bring your own protocol. You can use our own entanglement distribution protocol or teleportation protocol is available as an emulation tool, and you can get your hands dirty if you are interested. And basically there is a workflow for that. You define your network use case and protocol and algorithm, run your simulation, analyze, and then you can even implement in our testbed if you like to. So, and validate your example. So we have all APIs through the cloud available to our all equipment that we have developed inside the lab. If you are interested, this will become like a Qiskit in IBM, available to public, but that would be a first quarter of next year. If earlier you are interested, we are selectively make it available. Please contact me. We are happy to make it available to academics if they want. So with that, I finish my talk. I hope I was on time. I would say that we are building a practical, useful, and inclusive quantum network for all. That's the motto of Cisco, at least, would like me to advertise. Thank you.
Can you hear us?
Yes, I can hear you very well.
So I'm George Papin. I'm the moderator for this. Floor is open for questions for our speaker.
Thank you.
That's Karen.
Can you hear me?
Yes, you can hear.
Okay. Hi, Reza. This is Karen Bergman.
Hi, Karen.
So my question is, could you give us a sense of where the current status is on the hardware implementation of let's say the quantum data center, right? Like, do you actually have X racks that are connected with your optical switch?
At the moment, we have a processor connected, but no, I mean racks as you call it, a data center rack in a classical sense. No, we don't have it at the moment, but we have a processor connected. Yes.
So just as a quick follow-up, what's the timeline for having the full data center? Even the small.
The timeline, because Cisco is not developing quantum computing, and the timeline is based on the Cisco's partnership with his partner on quantum computers. We have a partnership, both small and larger vendors. Unfortunately, I cannot comment on that, but the timeline that I can comment for you, our major bottleneck at the moment for network side is the switch. We haven't still managed to fix our switch design, and mainly because of the both manufacturing process and the material. Because for us, I mean, the source has been solved. We have come up with a design which is repeatable, manufacturable, and we are happy with that. Commercially can be produced. But with the switch, at least, although lab-based, we have a quite good success. But from something that can go as something that can reasonably say repeatable process is not there. So that's the bottleneck for us for switch. But on the processor side, since it's a partnership with the other vendors, I cannot comment on that. Sorry.
Thank you.
Okay, let's thank the speaker again.